everybody. Welcome to the Riot Lunch and Learn series. My name is Caroline Griffin. I am Events and Operations Manager for the Riot organization, and we are very thankful to have you here with us today. We have a very exciting Lunch and Learn lined up. We have Aparna Spralik from the Aurora group, and we also have Dylan Howes and Susan Servinak from the TT Electronics organization. Just a couple reminders before we get started. If you have any questions throughout the presentation, please do put those in the chat box. Aparna and I will make sure that all of your questions are answered. And this will be recorded and posted to Riot's YouTube channel and meetup group, so you'll be able to catch that there after the presentation. But without further ado, I will hand it over to Aparna. Thank you for being here today.
Thank you, Carolyn. Appreciate the introduction. So today we will be presenting information and power conversion considerations for IoT applications with Power Partners, a TT Electronics company. Power Partners TT Electronics company is one of the companies that we represent in the Southeast. And I'm going to give us just a few minutes about the Aurora Group. We are a manufacturer's representative company. We've been around for over 30 years, and we have a lot of experience in electromechanical components. You may have seen us around in various trade shows and possibly visiting you as well. What we do, we work on behalf of the OEM and the customer principal manufacturers to create solutions that can fit your needs. So if you need samples of electromechanical components or need advice, we assist on those areas. Also help with custom solutions. We can get involved deeply on tolerance assessment, new designs, material issues, supply. And we also support all the different segments from IoT, telecom, aerospace, lighting, robotics, and various engineering projects. I like to you can think of us as a one-stop shop for advice on components. And of course, we deeply support in the supply chain area as well. This is just a brief look at the map of where we're located. We're in the Southeast and Florida areas where we support in the Aurora Group Southeast. This is just a brief look at our team. Many of them you may already know. So Bob, myself, Bob Ball, Kathy, and Ken are in the Carolinas. Bruce is in Tennessee, and Karen is in Georgia. This is just a brief look of all the manufacturers that we support, and highlighted here today is TT Electronics Power Partners. We're also very connected with all our different trade shows and organizations in the area, so you probably see our faces at these locations as well. And of course, we work with all our distribution partners. Again, we get involved with magnetics, mechanical components, capacitors, touchscreen displays, all kinds of hardware, including gears, sprockets, shaft locks, machine springs. Get involved with connectors, motors, thermal solutions, and more, of course. And of course, frequency control devices as well. I'm going to now introduce Dylan Howes and Susan. Susan is Director of Sales at TT Electronics. She's got a long history there in building that company and merging with TT Electronics last year. Dylan Howes is the Engineering Manager at Power Partners, and you may have seen him speak last year at one of the events that was nearby in Raleigh. Dylan is the Engineering Manager of Power Partners, and he is responsible for managing all technical aspects of power conversions and in the design effort and modifications. One of the best things about Power Partners is that if there's modifications that are required to any one of the power supplies, that they're right on it, and they can also do some updates or pre-testing, I should say, for the compliance that's needed. And with that, I'd like to turn it over to Susan to tell us a little bit more about Power Partners, just a few slides there, and then we'll get into the meat of what Dylan's going to present. And if anybody has any questions at all, I'll be monitoring the questions and asking them periodically and trying to answer them periodically throughout the call. Welcome, Susan.
Thank you. Thanks, Aparna, and thank you to everyone who's joined us today. I'm missing the slideshow now on my screen, so hopefully everybody else can see it.
No, I'm working to pull it up right now, Susan.
Okay, thanks. Awesome.
Should be back right now. You have it now, Susan?
Yep, I do have it. So the topic that Dylan will speak to you about in depth today is about power conversion and a particular area of focus on the IoT applications. I wanted to just give you a quick overview of TT Electronics. Power Partners is one particular group within the TT organization, which is a very large global group that specializes in the electronics industry. We do power supplies, we do connectivity, we do custom human interface solutions, and we also have the capability to build your product for you when you do get your designs that go into some level of mass production on that. Our particular group is located in Boston, Massachusetts. We are represented very nicely by the Aurora group down in your territory. Just bear in mind, we're a global company. We're about $500 million as of the last public announcement of our revenue on there. It is a company that takes a lot of that revenue and invests it in technology for the future, in our products that we bring to market, and also in our capabilities that we have to offer to you, which we can talk about a little bit on the next slide. You driving, Dylan? Thanks. Awesome. So like I said, our Center for Engineering and Collaboration on the power supply forefront is located in our Boston office, which is actually in a suburb out in Hudson, Massachusetts. The thing that I want to stress to you, and I think Aparna touched on this in her opening comments, was our ability to modify product for you and tailor it exactly to your needs. The statement on the left is very true. We'd like to be an extension of your engineering team and be your power supply department for you. We know that not every company out there, especially those that are just starting up and coming up with a concept of a design, can afford to have a power supply engineer on staff. So we loan ourselves to you for a day, a week, a month, whatever it takes for you to realize your goals for your power supply requirements and for us to bring them to life for you. We start with a clean piece of paper of what you're looking for. We try to work you into our best off-the-shelf solution. And if that doesn't meet it for you, we will go ahead and work with you to customize it to your need. We give you responses within 24 hours. There is a ton that we can do at that lab there in Hudson for you. Helping you to characterize your load, helping to work on those modifications for you, helping you with some issues that you might be facing when you get your product out to the EMI lab. So we encourage you to have that type of direct, in-depth dialogue with us. And you can always feel free to reach out to either Dylan directly for that type of help, or you can reach out to me or to Aparna, and we'll be there for you. So I'm going to let the man of the hour step in now and talk to you in detailed depth about power conversion. Thank you for your time.
Thanks, Susan. So I'm noticing that there might be some small amount of lag here between when I change slides and when they come up. So if I start talking about something before you see it, understand that I'm aware of that. So we're going to spend time talking about power supplies today, and specifically how we want to specify or what we want to look for in power supplies for IoT, Internet of Things applications. There's a lot that we're going to dive into here, so I'm going to try to go through a lot of these subtopics pretty quickly. I'm sure that the slides and the video will be made available after the presentation, so you can always go back and reference any of the equations or more of the minutia that might be through the presentation at a later time. So the first thing I wanted to touch on is just kind of take a quick step back to the basics to kind of build the framework of where we're starting here. And the key idea, right, is that we're going to be talking a lot about power and energy and power conversion. And these are concepts scientifically that have never changed, right? So we're entering the fourth industrial revolution now, and all the basic physics involved here are the same as they were before the first industrial revolution. But what has changed is how we convert, store, transfer, use energy and power. So specifically today, we're talking about electrical to electrical power conversion, right? So we want to change the IV characteristic, basically with some black box system here, where we've got a cross product and a cross variable and a through variable on either side of the black box. And the product of the cross variable and the through variable are going to be equal on both sides of that black box, in the ideal case, of course, where there aren't any losses. So we're working on mostly, at least in our world here at Power Partners, AC to DC power conversion, offline power conversion. All of our power converters and all modern power converters in general, unless you're dealing with very low power levels, are going to be switch mode power converters. And switch mode power conversion is not at all a new concept. This kind of technology has really been kind of around since the 1950s, but our implementation of this concept has improved significantly over time, and the components that are available to us have improved as well. So the fundamental concept here, and I've thrown up probably the simplest kind of switch mode power converter and an idealized schematic here with just, a handful of components to get the point across. The main concept of what we're doing is we're taking some voltage source, we're breaking that voltage source or that energy source up into discrete chunks, passing it over to the secondary, whether that be through an isolation transformer in an isolated design, or just straight into the secondary if it's a non-isolated design. And then we're filtering those chunks of energy through a low pass filter to give us DC again. So that's really easily exemplified with a non-isolated buck converter, where we've got some high voltage VA. We operate our switch shown there at some frequency and some duty cycle. And then our output across the capacitor is going to be that square wave of our T on over T on times T off, T on plus T off rather, multiplied by that original voltage. So we're able to adjust our IV characteristic. Now we've got more current available at the output. Our power is going to be the same if there aren't any losses on the input and the output. But what's ideal here is that we're only taking chunks of energy as we need them, as opposed to in a linear converter, where that through variable, the current, is going to be the same on both sides of the converter. And then we're obviously any difference in voltage and therefore the associated power is going to be burnt off as heat. We don't have to burn all that off as heat in a switch mode power supply. And that's what's interesting about switch mode power conversion. So in switch mode power conversion, we've got dozens of topologies and we've got dozens of variations on those dozens of topologies for different power levels, input voltages, and requirement sets, right? But they're all going to be using the same basic principles of breaking that energy up into chunks and transferring it, and the same essential hardware building blocks that we're all familiar with. So we've got, energy storage elements and switching elements. That's where all the magic is going to be happening. And then how we control and how we time these elements gives us our topologies and our net results. So jumping forward into what we actually came here to talk about, Internet of Things applications. I've got kind of a high level view of a power system associated with an Internet of Things application put up on the screen right now for you. So the way I kind of look at this, right, is we start from the outlet with our hazardous voltage source, and we're going to take an offline AC to DC converter, and we're going to send that DC voltage to some, downstream mains powered hardware. Within that mains powered hardware, we're probably going to be doing additional power conversion, DC to DC power conversion, so that we can send, different voltage rails to our Bluetooth chip or our Wi-Fi chip or whatever processor we might have inside of that device that are all going to be running off of different voltages. And then we also have in IoT systems remote elements. So when I think about the mains powered hardware, I'm thinking in my home, at least, of sort of like your Amazon Echo, right? Where you plug that thing into the wall and that's where all the magic happens. But you also have remote elements. You might be powering some sort of LED light, or I think of also my alarm system at my house. You might have some battery powered sensors, to monitor doors or windows or motion. So these are kind of the main elements of your typical IoT system and where power conversion lives with inside of them. And we're going to want different things. We're going to have different requirements from these different subsystems. So these are some high level kind of overviews of what we're going to want from these subsystems. Obviously, when we're dealing with an offline AC to DC converter, our primary concern is going to be safety because we're dealing with hazardous mains. And everything that's shown here on the left in this bullet is obviously stuff of regulatory concern. When we're dealing with AC to DC power conversion, the regulatory authorities get involved and they tell us, we have to meet certain EMC guidelines, we have to meet certain efficiency guidelines. But as the system designer, we're also interested in swap optimizing these devices, right? So size, weight, and power optimization. Everyone's always striving for higher function densities. In our industry, that means striving for higher power density. When we want to put more power conversion into a smaller package, that's always the goal. Obviously, circuit protection as well. We want the power supply to protect itself, but we also want to protect those downstream mains powered hardware devices from any sort of overvoltage event or anything like that. Inside of our downstream mains powered hardware, Primarily, what I think we're concerned with, with our power conversion is efficiency, so less heat, right? We don't want to be generating a ton of heat inside of our enclosure and cooking all of our components, and that contributes in some way too to reliability. We want these products to be reliable, and in all cases, we want them to be as small as possible for the maximum power conversion. Similarly, with our remote elements, pretty much the same list here, but now we're concerned about maximizing that battery life. So some of these applications we're dealing with, you want your batteries to be able to last for years sometimes. So the more efficiently we can convert power, if we're converting power inside of these sensors at all, depending on the application, the more efficiently we can do that, then the longer battery life we get out of them. And if you take all of these basic requirements and you can kind of categorize them into a few basic subtopics here. And the first one that we're going to talk about is efficiency and quiescent consumption. That's going to tie into our heat, our battery life, our efficiency compliance, and the reliability of the system. And it's a major topic for power conversion and IoT applications. Jumping right on into that, what I've got on the left here, or I'm sorry, on the right is your typical switch mode power conversion efficiency versus load curve. And this is an important curve to look at. This is actually an artificial curve that I've generated just mathematically, but it is indicative of what modern switch mode power conversion efficiency curves look like. So you basically ramp up really, really quickly from obviously no efficiency at no load, all the way up to some peak efficiency somewhere between 30% and 70%, and then it starts to taper off at the tail end again here. And what's interesting in IoT applications is that many of our devices are spending a majority of their time in either a sleep or a deep sleep mode, a standby mode. So if the majority of our duty cycle or the majority of our product lifetime is going to be spent in these low load states, and that's where our power converters are least efficient, then it's kind of silly to be proud of ourselves for using a 94.5% efficient power converter if in reality we're spending most of our time operating that device at 45% efficiency. Sure, go ahead.
Sorry to interrupt. We have a question
sure.
exactly about the battery supply. So it says, the question is about engineering a battery supply for ordinary power draw, but in few instances a peak draw. So just talk about exactly what you're talking about, low power draw and the battery supply with that. You can see it in the chat. And then
I don't have the chat pulled up, but I can speak to that quickly, just a little bit, and maybe whoever asked the question, we can continue the dialogue offline after, because I think speaking on that topic in particular, we could do maybe a 30 to 45 minute seminar on that as well. But that's actually one of the main modifications that, and we don't deal much with battery powered converters. We don't do a ton of DC to DC power conversion at Power Partners. But one of our main modifications here at Power Partners is adjusting our converters for peak conditions. So a lot of times you don't want to be in a situation where you say, okay, I've got a peak load of 10 watts, say, and so therefore I buy a 10 watt power converter. That's obviously going to be a lot more expensive to design than if your consumption over time is 1 watt. You'd like to be a lot closer to 1 watt when you buy that. So a lot of that primarily comes down to thermal management of the semiconductors and analyzing, how long are we spending in that higher conduction state, and how much energy are our semiconductors dissipating. If we can mark whoever asked that question, and we can follow up via email and see if we can have some more technical dialogue about it. Awesome. So jumping back in, if the total energy that we're going to be dissipating over all time is the sum of the power output over the efficiency in these different operating modes across this load, then really what we need to do is focus on improving efficiency where we're spending the most of our time, right? So that's the primary IoT objective here. At least for the majority of IoT applications that I'm familiar with. There may be some exceptions to that as well. So these next couple of slides, I want to make clear, I'm going to whip through these really, really quick, and there's a lot of content on the slides. What I really want to focus on is how the loss mechanisms inside of a modern switch mode power converter are related to the throughput, because that's going to tie back to how we get the shape of this load versus efficiency curve. So some of our primary losses are conduction losses inside of semiconductors, right? So this is when we have functional currents flowing through the effective equivalent resistance of a transistor or the effective forward voltage of a diode. And we can mitigate these losses in higher power applications via synchronous rectification. A lot of times we're making these better by using wide bandgap semiconductors, or just larger semiconductors if we can afford to do so. Again, the key to focus on here is the fact that we've got an I squared relationship, right? An ohmic relationship with power. So, well, that's obviously if we have a fixed resistance, but when we talk about a diode, now we've got a linear relationship with load current. So as our load increases, we have a linear increase in losses according to the forward voltage of those diodes, which are used regularly as for rectification on the secondary side of the converter. Again, not going to dwell on these because we've got a lot of them to go through, but just focus on how power losses relate to the load. Another major loss is switching losses inside of our semiconductors. So obviously our semiconductors are real, not ideal. So they do have periods of time where the product of the voltage across those elements and the current through them are non-zero simultaneously. This happens in the ohmic region for transistors or during reverse recovery in diodes. So those losses are going to be proportional to switching frequency. In some converters that are more the green mode converters, we're actually going to be adjusting our switching frequency as we adjust load as well. So we might be operating at a lower frequency at lighter loads or a higher frequency at higher loads. So there may be some impact there. It's usually a good way. Switching losses account for a lot of our light load losses. So if we can improve switching losses, then we can improve our quiescent consumption and we can improve the left side of that efficiency versus load curve. And I'll show exactly what I mean about that in a moment here. But again, these losses are proportional to switching frequency as shown. This is just a pictorial demonstration of how the switching losses actually occur inside of our semiconductors during switching. So for a transistor shown on the left rather, we've obviously got this parabolic, power curve here when we go through the ohmic region, and then the voltage across our transistors is never going to be zero. So in the conduction phase, we do have some losses that continue onward, but obviously the majority of the losses, the area under the curve is greatest during the switching cycle. And then inside of our diodes, obviously as charge carriers get swept out of the depletion region, we do have some period of time where the voltage across and current through the diode are non-zero simultaneously, and we get another one of those big parabola-shaped things there on the side. So if we can eliminate or reduce these switching losses, we can greatly improve our light load efficiency. Some of the ways that we're doing this that I'll touch on quickly, one of the most effective methods right now is soft switching, which is where we're using more advanced control techniques and basically better semiconductors to time the switching transitions to occur when either the current through or voltage across these elements would naturally be zero. And if we can do that, then we can force the power during the switching to be zero. That's incredibly effective, but it does require a lot more of a complicated design process. And as we started to get into resonant conversion, it's going to reduce our design flexibility as well. So if we want to, create a power converter and market it for 5 volts, 12 volts, 15 volts, this whole range of voltages, those are all basically going to be brand new designs as opposed to just rewinding our transformer. So it becomes a lot more costly on the R&D side. Another really good way to mitigate this is using burst mode operation. There's a couple different names for burst mode operation, but basically what we're doing is all of our power, I've got a slide showing this here that I'll pull up. Okay, there it is. So all of our power converters are basically regulating the voltage by modulating the duty cycle, typically. There are some frequency modulation converters as well, but typically we're modulating our duty cycle. However, you can only drop your duty cycle so low, right? So if we have a very, very light load and we drop our duty cycle down to 1% or 0.5%, we're still making the same number of switching transitions per cycle, two transitions per every single cycle. So what we have to start to do, if we don't need to have all these cycles, is drop them entirely, and that's shown in the scope captures down at the bottom there, where we basically apply a gating signal to all these high frequency switching actions and only use some of them. I'll go really quickly through the magnetics losses because these aren't going to play too largely into what we talk about going forward, but most people are familiar with hysteresis loss, right? This is also proportional to switching frequency because the atoms inside of the magnetic material have to be realigned during every switching cycle, and realigning those atoms takes energy. So that's proportional to switching frequency. We've got core losses, eddy current losses inside of our magnetic cores because they're not only magnetically conductive, if you want to call it conductive, but they're also electrically conductive, right? Now, these losses are pretty difficult to mathematically correlate to load condition, which is the goal of what we're talking about here. But if you were to take an estimated, stab at it, it's going to be approximately linear to duty cycle, where you have an on-time impact, how long you're actually conducting with the losses inside of the core. So that's going to be linear with load approximately, but it's also not a super large component of the loss inside of a switch mode power converter. Some of the ways that we can mitigate this, right, are using powder cores or core laminations to put smaller potentials across higher impedance sections of core material. One other really common magnetics loss that we do a lot to mitigate, at least in our AC to DC world, is the skin effect. So as we increase our switching frequency, we're going to be, the magnetic field is going to be forcing charge carriers inside of our windings to flow closer to the surface of those materials, which effectively reduces the surface, or effectively reduces the cross-sectional area of our conductors and increases the impedance of those conductors. One of the best solutions to this is to use flat windings. So if all of our charge carriers want to flow at the surface, then why don't we make our entire conductor essentially surface area? So that's a really effective strategy that we do use in some of our primary filters or even transformers. And this, again, this is proportional to your switching frequency. So as your frequency goes up, your skin depth is going to get, well, your effective area is going to decrease and your losses will go up. And then in external power conversion, offline converters, one of the main loss mechanisms is just simple conduction losses inside of traces on the secondary side of the converter and inside of DC cables. So if we've got a long DC cable with thin gauge, we're getting a ton of losses there. That's one of the most dominant mechanisms when we get into higher load conditions. So focus again here on the fact that this is related to the square of the load. So we rushed through all of that, but the big picture that I wanted to land on is that we can basically sum all of these up. And one that I didn't touch on too thoroughly is the fixed losses. Things like what it takes to power our control chips, any dampening resistors that we might have in our EMC filters, any resistors that sit across the secondary side for sensing what the voltage is to send those voltage feedback signals to the primary. These things are always on and they're fixed no matter what our output load condition is going to be. Then we've got those duty cycle losses, or the losses that are going to follow linearly with our load. Those are really, really not dominant, or they don't have a dominant effect on the load versus efficiency curve, at least for our offline AC to DC switching converters. So we're not going to focus on those too much. And then as we get into the higher loads, obviously our load squared losses become dominant. So the efficiency is loosely, inversely proportional to the second order polynomial here. So what we can do is we can start to play with some of these figures to see how improving certain types of losses might help us flatten out this curve, which is the ultimate goal in an IoT application from an efficiency standpoint. So this is that same curve that I showed you before, and I've assigned arbitrary weights to the coefficients on this loss polynomial. And these, they may be arbitrary, but they're representative of real switch mode power converters. So this arbitrary converter has a peak efficiency around 90%. Really, that's probably maybe indicative of an offline adapter where you've got some pretty strong conduction losses. A lot of our internal converters, we're starting to push, 95% now, but this is still reasonably representative. And what we see is that as we start to reduce, it's intuitive, as we start to reduce those conduction losses by improving, how our I squared power losses. So we start to flatten the end of the curve and bring it up. And I've got that displayed graphically here. So reducing from that arbitrary 8% value down to maybe 5% or 2% of our full load losses, we start to bring the tail end of that curve up and flatten it out. Perhaps more interestingly or importantly for IoT applications is what happens when we start to reduce those fixed losses by using green mode converters and by dropping cycles or using zero voltage, zero current soft switching. And that has a drastic impact on our light load efficiency as displayed here. So before I made the example that, hey, in this arbitrary standby mode that we talked about, we were operating between 45 and 55% efficiency, wasting half of our energy most of the time. By reducing those light load losses from say 3% down to 2%, down to 1%, we drastically start to bring the butt end of that curve up and move that knee closer to the left. Now we can say maybe we're operating at 75% efficiency down in these light load states. So that's really the primary target if we're spending a lot of time in a light load or standby deep sleep state. So another item of concern primarily for our offline converters, for our AC to DCs, is all the regulatory constraints that are involved here, and also functioning off of global power sources. Because if we're building this IoT device, chances are we want to sell it to more than just the North American market. We probably want to sell it into Europe and other major markets around the globe as well. I'll start by saying I did not generate this nifty little colored map here. I stole this off the internet from a company called Sailwider Electronics, so I just want to credit them for that real quick. I did make it really messy though in the next couple of slides. So this just gives you a quick graphic representation of what different line voltage levels look like around the globe. And it's a mess if you're trying to design for these, right? Luckily, it's become a lot easier to design for universal mains with the improvement of semiconductors over time. But obviously in North America, we're used to our 115 volts at 60 hertz. Throughout most of Europe, we're operating on 230 at 50 hertz. Then we've got our oddball regions like South America, where it's all over the place. And of course, there's always Japan, running down at 100 volts, which can make things a little bit complicated for power supply design, especially if we start to talk about in-home healthcare applications. But that's kind of neither here nor there. But that's the map of voltages, line voltages across the globe. So to further complicate this map, we have regulatory constraints, right? So obviously there's some international governing standard, and we will talk about what that standard is in a moment, that tells us how we have to build these power converters safely. But then every nation wants to put their own stamp of approval on it as well, right? So the ones that we're probably familiar with most are UL, and then the CE mark, Declaration of Conformity, over in Europe. But there is also obviously, NOM for Mexico, CSA for Canada, EAC for Russia. People are familiar with the PSE mark in Japan, CCC in China. So depending on what your application is and what your market entry strategy is, you might need to get a swath of agency approvals that are essentially all saying the same thing on your power converter to sell it globally. And then further complicating the map somewhat, although maybe not so much for us here in the US, is the fact that most of these regions also have mandates on how efficient your power converter needs to be, which is something that we kind of just went into, not from a regulatory standpoint, more from a technical standpoint, but every region is going to be saying you have to meet some sort of, eco-design directive or Department of Energy law. So this is a pretty messy map to try to sell into, right? So from a technical, we'll come back to that regulatory stuff in a moment, but from a technical standpoint, when we're talking about different line voltages around the world, most people are probably familiar with the fact that universal rated mains are going to be 100 to 240. So if you take a look at most of your power bricks or wall mount adapters right now, you're going to see 100 volts to 240 volts, 50 to 60 hertz. People are familiar with that. The actual product performance, though, is going to have to allow for 10% deviations on that line voltage and 3 hertz deviations on the frequencies. That gives us what a true universal mains converter is, input needs to be, which is 90 to 264 volts AC at 47 to 63 hertz. From a technical standpoint, like I said, these challenges have become relatively easy to handle with the improvement of semiconductors, current handling and voltage handling of switches. But the things you do need to consider if you're designing one of these are that obviously you need to size your semiconductors in your primary. For series currents, when you're operating on 90 volts low line, you're going to have higher primary side currents. You need to account for that. The dual to that, or the inverse of that, I guess, is if you're operating on high line, the maximum voltage 264 volts, your currents are going to be lower, but obviously now you need to be able to withstand those voltage stresses on the primary side of your converter. You also have to size your transformer for peak currents that are going to be much, much higher on 240 volts or 264 volts, and you don't want to saturate your cores when you're operating under those conditions. There are also topological constraints on duty cycles. So you can't always just ramp your converter up to 100% duty cycle and leave the switch on. It won't work anymore. I think that's intuitive. But so depending on what topology you've chosen, you're going to have some maximum duty cycle that you're allowed to operate at. So if your line voltage gets lower and lower, you can only bring the duty cycle up so high, you're gonna start to have your converter shut down, or your output start to drop. One less technical but more mechanical kind of item I wanted to throw out there, an easy solution if you're using an offline wall mount sort of adapter might be to consider a universal converter with interchangeable AC blades. So you guys have a lot of people have probably seen these where you can pop the plugs on and off, put in a USA, put in an Australian, put in an EU. If those are globally certified, that's a really easy market strategy to reduce the number of SKUs that you've got in your BOM. Another thing that we think about, or at least that comes to my mind when we talk about universal mains, is the harmonic current standard and power factor correction. So this is going to be something that's, if you're selling into Europe, is going to be applicable to anything that's 75 watts of throughput or greater. I'm not sure that everyone knows exactly where power factor correction comes from or why we have to do this. I've drawn a really, really simplified schematic of the front end of an AC to DC converter, right? Where we've got some AC source, some rectifier, which is typically going to be a full bridge rectifier, and then some giant bulk capacitance. So what happens here is as that capacitor charges up and develops some potential across it, we're going to start to have discontinuities in the current that flow from the AC source through that rectifier. If the voltage on the AC source falls below the voltage that's currently stored on the capacitor, no current is going to flow. So we're going to start to get a ton of harmonic content on our AC mains, and that causes dirty power, and so it needs to be regulated. So there's tons of regulations all the way out to, I forget the exact number, I think it's either the 43rd or 45th harmonic of how much energy we can actually conduct back onto the mains. So the simplest solution to this, and the one that the industry has adopted for active power factor correction, is to put a well-controlled boost converter between that rectification element and the bulk capacitance. So basically this boost converter is going to have a feedback input that is proportional to the current AC voltage, the current mains voltage. And we're going to force our switches to operate such that the current drawn from the mains is proportional to that voltage. And what that basically does is it turns our current into a sinusoid that's perfectly in phase with the voltage, and it drives our power factor towards 1. So I realize now that I didn't label these plots up here, so you might be wondering what they are. The top plot is the AC waveform. The second plot is the voltage across the capacitor that's charging up when the AC waveform is going positive, and then discharging when the diode is reverse biased through the resistor. And then the bottom trace is the actual current being drawn off the mains, and that's where we see that discontinuity that is going to have a ton of harmonic content in it. The complication here in how it relates to universal mains is that in order for a boost converter to work, the output has to always have a higher voltage than the input. So if we expect our input to be 264 volts, the peak value on that is, root 2 times 264 gives us 373 volts. So our bulk voltage, our high voltage bus for a universal converter has to be above 373 volts. And typically we're using about 400 volts, between 400 and 405 volts. And that's because we're using 450 volt rated capacitors, and we want a good 10% safety margin there. Jumping into safety, basically the governing standard for any industrial application, any IoT application, as of the end of this month, actually, this is coming up real time right now, is IEC 62368. So 62368 is the standard for safety of information and communication technology. This is superseding what many people are probably familiar with, which is 60950, which was the governing standard for the industrial power converters for many years leading up until this point. It's being withdrawn with a hard stop in Europe at the end of this month, in December 2020. And in the US, we're doing a soft transition, which ultimately, with everyone selling to the global market, doesn't actually really make all that much of a difference. So 62368 is the standard to go with if you're certifying a product to industrial standard at this time. Just like any other safety standard, basically all this is ensuring is that we're keeping users safe, right, from electrical, thermal, chemical, and mechanical hazards. And this is pertaining specifically to our offline AC to DC converters. Those converters always have to be isolated, right? We can't have a galvanic connection between the hazardous AC mains and the secondary supply that you might grab with your hand. And our secondary is almost always, at least in my industry, we're going to be dealing with SELV networks. So that's anything that's under 60 volts DC. You get over that and it starts to be considered hazardous to a user if they touch it. We obviously want to continue to mitigate our component temperatures, not only for reliability, but also to ensure they don't catch on fire if someone's running their AC to DC converter next to a pellet stove or something. The first step when we looked at that regulatory map with all the different marks, no matter where you want to sell this product, the first step, obviously, as with many things, is to get a CV scheme certification against the international standard, the IEC 62368-1 standard. And then obviously, North America being a major market, the major market, I'd say, for most applications, you need to get an NRTL certification as well against the UL version of that IEC standard. Now, usually if you're certifying your supply or your system to IEC 62368, and you're recognizing a good, good amount of those national deviations, you're not going to have any additional issues certifying to the different country-specific standards, other than, of course, paying the $10,000, $20,000 a pop that it is to certify to those. And those may be required for certain regions, so keep that in mind as well. Electromagnetic compatibility standpoint, basically we need to ensure that our converters are giving us plenty of margin for additional radiated and conducted emissions that might be contributed from the downstream electronic system. The governing standards for industrial applications, for IoT applications, are going to be EN 55032 over in Europe, CISPR 22, and then here in the US, FCC Part 15 Class B limits. We want to be meeting Class B limits. And the rule of thumb for most applications is 6 dB of margin, right? But if you want 6 dB of margin in your application, you're probably going to be looking for more than 6 dB of margin from your power supply, because your system will most likely contribute to those emissions. From an immunity standpoint, obviously we don't want electromagnetic energy to take our converters offline. So the basic set of requirements here against the 61,000 level testing are to have an ESD immunity of 8 kilovolts air discharge and 4 kilovolts contact discharge. In all honesty, with a power converter, that's pretty easy to accomplish because of all that bulk capacitance. ESD doesn't really stand much of a chance of hurting most of these converters. Radiated fields of 3 volts per meter, fast transients, EFT is going to be 1 kV. We want differential mode, surge protection of 1 kilovolt, and common mode, surge protection of 2 kV. Your conducted RF energy immunity needs to be at least 3 volts RMS. Power frequency magnetic field, that's a fairly easy one, 1 amp per meter. And then your dips and interruptions as specified there as well. So in order to, the big challenge, the immunity is not really so hard, at least with offline power converter design. That's kind of tried and true and been done for a while now. What is important is trying to look for quiet topologies that aren't going to be conducting a ton of energy back onto the mains or radiating a bunch of energy. We've had a lot of luck with one of our new designs that uses a resonant half bridge topology and drastically mitigating those conducted and radiated emissions. And I'll talk a little bit more about that in a moment. You also want to look for go ahead.
A question that's relevant to the compliance. This is from Mark. It is a 60 volt from the US NEC for low voltage a global standard? Is that globally typically peak or RMS?
So whether or not it's global, I believe it's defined that way in the international standards. So I think that should be considered global. It's 60 volts DC and then whatever 60 over root 2 is for AC. So I guess the answer to that question then would be not RMS, it would be peak.
Peak, okay.
I think it's, I don't know the exact number off the top of my head. I think it's something like 48 point something volts AC for SELV networks. And that stands for safety extra low voltage.
Okay.
You do also want to look for well-filtered IO. And that's not necessarily, I'm not saying tear apart your power supply and check out what the common mode choke looks like. But as long as we're keeping high frequency energy, or maybe do that, I don't know. But as long as we're keeping high frequency energy off of our radiators, our cables, that's going to drastically help with our radiated emissions profiles. Talked about efficiency more than enough already, but this is just, again, another snapshot of what the efficiency levels around the globe are right now and what legislation ties into those standards. Sort of the golden rule, and I'm weary to say that, and I'll explain why on the next slide, is level 6 efficiency, DOE level 6. That's what is basically the highest regulated standard right now for offline power converter efficiency, which regulates your quiescent consumption depending on your power level, and it also regulates your average active mode efficiency. What's the efficiency of your converter? 25%, 50%, 75%, 100%. Average those conditions out, and you get an average active mode efficiency. Now, even though, one thing I do want to point out on this slide, even though the US and Europe are kind of leading the charge here with the level 6 requirement, you might say, okay, so I have no problem entering the Korean market or the Australian market because they're only requiring level 3. They have their own specific standards for exactly how you have to test that. So even though the efficiency requirements are way, way lower, you have to do it on their exact line voltage by their exact test methods. So there's still money to pass forward if you want to certify your energy efficiency for the Australian or Korean markets. Even though you say, I've got a level 6 converter, I'm obviously going to pass. You are obviously going to pass, but there is still a certification process there. So this is why I was weary to say that level 6 is the golden standard. For power supply manufacturers, the golden standard has actually kind of become COC tier 2. And the reason for that is because we were all under the impression that COC tier 2, which is significantly more stringent than DOE level 6, was going to be put into effect at the end of 2018. So we all rushed into trying to comply to this thing. We redesigned half of our AC to DC converters. We spun new PCBs to make sure that we can meet this new energy efficiency requirement. And then it disappeared. The member states couldn't agree on exactly how they wanted to implement it. And there's no law saying that anyone needs to meet COC tier 2. So it's become nothing more, I guess, at this point than a marketing standpoint. We can say, hey, we have the most efficient power converter, it meets the most efficient standard. And what is important to note is that someday that's obviously going to become law, right? We're always progressing these things forward. So that standard is currently the most stringent recognized standard. So it will eventually someday become law. So you might want to look out for using a COC tier 2 compliance supply for your international sales. Okay, I'm not sure exactly how much time we have left here, not a ton, but the last thing we're going to head into, just other topics, and I'm going to focus most of that time primarily on size, weight, and power optimization, because people are always interested in getting, like I said, higher function densities. We want to pack more power conversion into a smaller package. What are the trade-offs there? What are the challenges, and how are those maybe being addressed? So the first question I want to pose, and I can't see the chat window, so this is kind of rhetorical, but if we look at an open frame power supply, what's taking up all the space? How are we preventing this thing from getting any smaller? And I think it's pretty clear right off the bat which elements are contributing to most of the space consumption. That's our magnetics. So on the front end, we've got our boost choke, which is huge. The transformer is the biggest element on the entire PCB. And our CM chokes take up a good amount of space in the back of the converter as well. Then we've got our energy storage, that giant bulk capacitor on the front end, and all of our filter capacitors out on the secondary on the left side of the converter there. It's tough for me. I'm not used to being able to not point at the slides, but you can see the secondary is off to the left of the slide, and there's a good amount of filter capacitance there. And then the third element that can take up a lot of space is thermal management. Increasing the surface area of our semiconductors, or effectively increasing the surface area of the semiconductors so that they can radiate their heat out to the environment more effectively and not burn up. Now, reducing the size of any one of these things is a trade-off with the others, and also sometimes with cost. So we'll dive into that. So the first big one, the biggest element on the board was the transformer, right? And so why does that transformer need to be so big? And the answer is really kind of simple, even though I've got a bunch of equations thrown up here. So we go back to the very beginning, power is the change in energy over the change in time. So if you take that change in time, and you put it in the frequency domain, we've got power is frequency times the change in energy. And then the energy that exists inside of that transformer or any magnetic element in a given period of time is a function of the number of turns, the current through it, the area, cross-sectional area of the core, the length of the core, and then the permeability of that material. But these are real ferromagnetic cores, and obviously they're saturable. So we can only play with I and N so much before we start to get diminishing returns. I've used G here to denote that the relative permeability is a function of I and N because I've already used F to denote frequency. So that just means it's some function of. So for a fixed geometry, we eventually have diminished returns. Now, if you boil this all down, you basically get that power is going to be proportional to the area of your core times the frequency that you operate at. And the way that I like to think about this really fast, if we're not going to spend a ton of time talking about the math, is the water bucket analogy. So if you need to move a ton of water from one place to the next, or a ton of energy from one side of the converter to the other side of the converter, you've got two options. You can either use a really big bucket, or you can make a lot of trips. So we still have to convert the same amount of energy per unit time. So the only way that we can do more trips is by doing more trips per unit time. So you get either a bigger bucket or lots of little buckets. So you get an area frequency trade-off. But the problem is that as we start to increase our switching frequency, we start to decrease our efficiency. Now we're dissipating more heat, right? So there's a trade-off there. The next thing, this slide's fun, is our EMC filters, right? We've got a ton of magnetics in our EMC filters, common mode chokes to keep high frequency energy off of the AC mains. So what's shown on the right here is a Dell 807 power supply, one of our TT Electronics power supplies. It is, I don't know exactly, it was probably designed before I was born, to be honest with you. So this is a 400 watt adapter. It's absolutely enormous. The blue box that I've drawn there is approximately the size of the entire converter on the left. Now, these converters are not exactly the same power level, so it's not a fair apples to apples, but it'll at least act as a visual reference as we go forward and talk about this, and how the choice of topology and how we're designing these converters drastically impacts how big we have to make our filters. So I talked earlier about the resonant half bridge. This is one of the reason I'm talking about it so much is because it's one of the newest products we released, and it's wildly impressive. It's 150 watt 2x3, super high power density, 21.5 watts per inch cubed. Again, that uses a resonant half bridge topology. If we look over on the right, that's an old forward mode topology, right? So it's got a much lower power density accordingly, but also note the relative size of the EMC filter. Our entire EMC filter on that PPWA is 15.5% of the footprint. And we've got more than 12 dB of margins. In fact, it's usually in some locations throughout the frequency band, it's actually up around 20 dB of margin against class B limits. It's silent. And it only takes up 13.5% of the footprint. On the other hand, the Dell 807, the older design, again, it's a very, very old design, and that's why, but it shows you how the topology selection is important here. We've got a filter that is the size of the other converter, and we are taking up 22% of the footprint of that entire converter, and we're scraping by to get 6 dB of margin. So we can reduce the size of the magnetics in our primary filter if we use a quieter topology, a soft switching topology. Capacitors, one thing I wanted to kind of note here, because you look at a power converter and you see how big that bulk capacitance is, and you might be tempted to wonder, why do we need that bulk capacitance here? And the short answer, the quick answer, is that supply lines are inductive and switching frequencies are high, right? So this example that I've plotted up here is kind of an extreme example where we're pretending that the mains are a brick wall for anything higher than, a kilohertz, I don't know, which is not necessarily true. But basically the idea is that we need to supply our switching network with high frequency energy. And we need to pull low frequency energy off of the mains because those supply lines are inductive. So we basically have to pull that energy in the low frequency world, store it locally, and then disperse it to our switching converter at a much higher rate of speed. Again, we have that complication where for universal mains, if we're doing power factor correction, our high voltage bus has to be higher than 373 volts. So if you work out how much energy you would need, assuming again that the mains are acting as like a brick wall at these switching frequencies, if you say, okay, I need to supply 100 watts for 100 milliseconds transiently to my load, that's going to be 10 joules, right? And if you work out how much energy you're going to have to pull off of that capacitor, assuming you can't pull any energy off of the mains, that equates to an 800 microfarad capacitor, which is a realistic value for the bulk capacitance on a fairly large power supply, maybe a 400 watt, 200 to 400 watt power supply. And we're rating that thing at 450 volts. So that's not a small cap. And obviously with capacitance, the size of your capacitor is going to determine the capacitance, right? If we're getting a higher voltage, then the distance between our plates is effectively going to be larger. And if we want more capacitance, we add surface area. So those caps are growing as we increase that capacitance. On the secondary, obviously we're putting those caps there to filter our ripple and noise. If we add more capacitance, we get less peak-to-peak voltage deviations on our output. It's not important for all applications. For some sensitive applications, you want that voltage ripple to be exceptionally low. One way that you can improve that is with more capacitance, taking up more space. There's one of the trade-offs. Another way that you can reduce that is by increasing your switching frequency, which again is another trade-off. If you increase your switching frequency, then you're going to reduce your efficiency overall.
So Dylan, we've got a few very good questions that have just come in. So one is, what is your experience with the higher frequencies? Oh, there we go. Higher frequencies for tighter PCBA integrated magnetics core utilizing low amounts of PCB traces and windings. This is going back to your topology question or your topology issue.
Sure. Could you ask the question again?
What is your experience at higher frequencies for tighter PCBA integrated magnetics, in parentheses, core utilizing low amounts of PCBA traces as windings?
I don't have any personal experience with that at all. What we can do is if we can get that person's contact information, we can talk to one of the R&D engineers and see if they have any experience with that. That doesn't sound like something I'm familiar with at all.
Okay. And there's two more questions that came out and it doesn't necessarily apply here. One of them was, does the TT team work with solar powered battery backed power conversion designs? So any power supplies that marry up to either battery backup or solar, especially
yes, absolutely.
Light EV charging solutions. That's the hot topic right now. And then, so yes, is the answer to that.
The answer, the longer answer is that our division in Boston doesn't do much work with that at all, but TT Electronics work. So interestingly, even though we're the power supply people, we actually sit inside the Internet of Things division, the IoT division within TT Electronics. TT Electronics has an entire other division called the Power Electronics division. That division is working a lot with that type of technology, and we can connect with that division as need be.
And then the other thing that goes along with IoTs is, of course, sensors. So does switch power sometimes put noise into the analog sensor or output application? How can that high frequency of switching be attenuated on the signal side?
Sure. And again, with any of these questions that are coming in, I'm happy to discuss them further offline. But yes, absolutely. The switch mode power converters are noisy by design, right? So, and there are ways that we can help. There are many ways that we can mitigate that. One of the simplest ways it sounds like they're asking about interfering with analog electronics downstream. A lot of times what I see people doing is just simple filtering, right? Just throw a bunch more capacitance and inductance at the output filter, the low pass filter. That's not necessarily the most elegant solution or the right solution for the application at hand. So I'd like to talk about that specific application, but there's more than one way to skin that cat. And yes, it absolutely can interfere with analog signals downstream.
I think that's it for the questions right now. So I would say continue.
Okay, excellent. So when we're getting to the end of this here too, I know that we're coming up on 2 o'clock, but I think I've only got a handful more slides for you. So the last item that we talked about taking up all the space was thermal management, and the Dell 807 makes an excellent example of this for us again. So again, this converter was probably designed before I was born, and I actually laughed the first time that I pulled this thing out of the warehouse and I saw the size of those heat sinks. Those big black boxes are they're each tied to 1 or 2 semiconductors, transistors, and data. So, and this is a 400 watt converter. But the idea here, right, is that the dissipation of our converter as a whole is going to be directly proportional to our throughput. And then there's a 1/over efficiency factor in there. So as we boost our efficiency, ideally if we boosted it to 1, right, which is not possible, then we would have no dissipation. So whatever our dissipation is based on our efficiency, we have to dissipate that into the environment somehow. So basic heat transfer principles, right? The amount of heat that we transfer from one material to another is going to be proportional to the surface area of that interface. So that's why if we need to dissipate more heat because we're less efficient, we need larger heat sinks. So if we make things smaller, we got to reduce the heat that they generate. So I'm making an example here. Again, the resonant half bridge is exceptionally efficient across the board at 94.5%. Again, not apples to apples because it's a 150 watt converter versus a 400 watt, but look at the difference in the size of the heat sinks. And it comes out in the math why that is. Operating at 94.5% efficiency, we're only dissipating, worst case, a little less than 9 watts for the smaller supply. The larger supply operating down at 80% efficiency, best case, we're dissipating 100 watts, almost as much as the first converter actually even generates or converts. So that's one way to reduce the size of your heat sinks, is to make sure that you're operating more efficiently. And the last topic that we're going to go into, and based on where we are from time, I think this is actually the most important slide of that topic, and it's what kind of protections do you want to look for from these converters, and how can they be implemented low cost, and what kind of response do we want these protections to provide? So the way that I look at this is, at least for commercial use, we want our Internet of Things devices to be transparent. So the whole idea is that we're making life more convenient, right? We don't want to have any kind of user intervention if there's a fault with one of our power conversion systems, if we can help it. And any of our non-serviceable elements, things that we would just have to replace, we want those to be safeguarded from damage. So if we have a cheap offline AC to DC wall mount adapter that, I don't know, maybe that's $10 in your BOM, whatever it may be, we'd rather throw that out than maybe the entire, downstream mains powered electronics. So we want it to protect itself, and we also want it to protect the downstream electronics. And these protections can be very, very low cost in these applications. There's no reason we need to reinvent the wheel on them. And I'll show that very quickly in the next few slides. But primarily, we want the converters to protect themselves from brownouts, over temperature events, and from overload events. And basically in all of these conditions, we want auto recoverable. We don't want the user to have to come over and cycle the mains every time there's some sort of fault. And that's very easy to implement, especially with modern control chips. These are basically inputs to the control chips that we're working with that you hook up a couple of passives to, and your solution is right there. The other type of fault that we want to look out for and maybe respond to differently is overvoltage. And I think a lot of the customers I talk to, sometimes, maybe I shouldn't say a lot, some of the customers I talk to get confused about why overvoltage response on a power supply tends to be latching. And the reason for that is because overvoltage events are typically coming from a breakage in the feedback loop that's going to drive the supply output to infinity. So if we start sending 1,000 volts at your device, we're going to fry all of your electronics, right? And resetting the power supply is not going to fix the feedback loop. So you got to basically cut your losses and turn the whole thing off for good. And we'll talk about that in a second here. So it's not really useful to have an auto recovery feature on an overvoltage protection. So make sure you're looking for, maybe your application is different, but in most situations, make sure you're looking for a latching overvoltage protection feature on your IoT applications. I'm not going to walk through all these. These are just examples of how easily these things are implemented. So I've highlighted basically how simple the little passives are to tie into a control chip. We're achieving brownout protection here with 4 simple SMD resistors and a cap going to a control pin on the control card on the primary side of the converter. Over temperature protection, same thing. We've got 2 resistors, a thermistor, and a diode off the auxiliary winding on the converter, ties into a control pin on the control chip. Simple, done. Overload protection is just 1 sense element and 2 filter elements off the main transformer, and you can implement overload protection. So, and again, these are all things that are built into the control chips that we're designing our converters with. They're simple, they're low cost. There are other ways to do these things. There are more dissipative ways to do these things. And in most of these applications, you want to strive for lower cost solutions. One that I really like to talk about is that overvoltage protection. This is an incredibly simple thing to implement if you make it simple. And it's just clamping your output with a zener and not power protecting it at all. And now we could be more complicated, and we could connect some sort of sensing and control network up to this, where we're basically sensing that zener is broken down, protecting the zener from destroying itself. Maybe there's a comparator in there hooked up to an optocoupler. We send a signal back to the primary. We tell the primary, hey, there's an overvoltage fault, turn off, wait for the fault to go away. great. Again, most of these things are not going to come back from the dead. So if you just clamp your output with a zener, when that zener fails, it's going to fail short. And now you just harness your overload protection to respond to that short circuit for all time. So one simple component will give you that latching over voltage protection. Just to summarize everything we've talked about, again, when you're looking for IoT power converters, efficiency and quiescent consumption is really king in this industry. So you want a nice, flat, high efficiency curve that's going to help us keep our heat down, improve our battery life, and improve overall reliability. It's also a regulatory concern as we sell our products around the globe. For safety, make sure you're looking for IEC 63668-1 certification. You want to be certified to EN 55032 and FCC Class B, FCC Part 15 Class B limits. With ample margin. If you can get more than 6 dB of margin, that's great. And DOE level 6 or COC tier 2, depending on which side you want to look at it, is kind of the golden standard for average active mode efficiency and quiescent consumption. You need to have universal mains adapters if you're selling outside of the US. So 90 to 264 volts, 47 to 63 hertz. Again, take a look at some of those offline wall mount adapters that have interchangeable blades. That can be a really simple solution, low cost solution for selling your offline power converter around the globe. And lastly, size, weight, and power optimization. And the key takeaway here is that improving the density of these power converters is a balance of all those different trade-offs. So you want to make sure that you're working with a power supply vendor who's up to date on modern conversion technologies and best design practices for minimizing those densities, or maximizing the densities and minimizing the area of the converter. That's the entirety of the presentation that I've put together. I realize we're right up at exactly 2:01. I'm happy to take any other questions. And I think most of the questions are probably best facilitated offline, especially if they're not something that I have direct experience with, but feel free to ask now as you see fit. Thank you.
Thanks, Dylan. I was just looking through the chat box here to see if there are any other interesting questions that have come up. Yeah, I think you answered them pretty well. Let's see. Yep. As a reminder to everybody, we will have this video available. I think Caroline will put it out on the Riot Education page. And it'll be available on YouTube, and I can certainly send it out. If anybody has any other questions, you can feel free to send an email to me or Dylan or Susan directly, and we'd like to help you out. Are there any more questions? Well, we got a lot of attaboys, Dylan, so it was really a good presentation. A lot of very detailed information on power supplies and what needs to happen, especially on the compliance side. So if there's no other questions, then back to you, Caroline.
Thanks so much, Aparna. Great presentation, Dylan. Thank you, Dylan, Susan, and Aparna. And thank you all for joining us today. As Aparna mentioned, I encourage you to reach out to her and to Dylan with any questions that you may think of afterwards or that you didn't have time to ask today. And this was recorded and will be posted to Riot's YouTube and Meetup channels. So thank you so much for joining. Thanks again, Dylan, Aparna, Susan. Everyone take care.
Thank you.
Thank you.